Hello, I'm Wilson Beloth, PhD student at Mechanical Laboratory of Normandy in Rouen in France, and I'm going to present to you the application of different surrogate models to quantify the uncertainty of wind turbine blade loads. This presentation is an early stage of the main thesis subject, that is the reliability analysis of a wind turbine blade using deep neural network. To simulate wind turbine blades is often used Aero-elastic Simulation codes as FAST from National Renewable Energy Laboratory or HOG2 from Denmark Technological University, because these tools couple the aerodynamic response with the elastic hydrodynamic control and electrical behavior using a beam representation of the wind turbine, leading to a nonlinear dynamic response. Using these simulation tools compared to computational fluid dynamics simulation, they have the advantage that a coupled response can be calculated for different wind conditions in less computational time because of the beam finite element model, contrary to CFD that needs a 2D or 3D finite element model. But as new technologies for data-driven models, as machine learning for example, they are evolving surprisingly fast. These surrogate models could be trained to replace the Aero-elastic simulation codes and be used to predict directly the behavior of the wind turbine, further reducing the CPU calculation time. The wind turbine blade used as reference is the 10 megawatts from Denmark Technological University, but with a simplified composite material distribution. In the cross-section, all shear waves have the same material distribution. Leading panel and nose are regrouped into one main region, and caps, trailing panel, and tails are also regrouped in another main region, having only 3 regions in the cross-section for the material distribution. In the span-wise direction, also 3 regions are defined with a constant material distribution. In total, 24 thickness different variables are defined to represent the simplified composite material distribution of the wind turbine blade. With this simplified 10 megawatts wind turbine blade, 2 different cases will be simulated. First case is a steady simulation. First, a random uniform wind steady condition is defined between 4 and 25 meters per second. Then, a 10 minutes aero-elastic simulation using fast code is performed to extract all the loads acting on the blade, forces and moment. Then, from the time history response is extract the maximum load value at each wind speed, and finally, 2 different surrogate models will be trained to predict these maximum loads values. Experimental data from Open Data NG Renewable Project is used as reference for the wind speed probability distribution. This data is collected at a height of 80 meters. In order to use it properly, the wind speed is shifted to the height of the 10 megawatts equal to 119 meters, using a power law and assuming a condition of air similar to the location of the reference 2 megawatts wind turbine from NG. The second case is similar to the first case, but the environmental conditions in this case are assumed to be unsteady, including changes in the wind speed, shear exponent, and misaligned of the wind turbine blade in the yaw direction. The same experimental wind speed distribution is used in this case, but also is defined as standard deviation of the wind speed extracted from the wind turbine standard IEC, a mean shear exponent based on a simplified relationship and a normal distribution for the yaw misaligned angle. Then, a Rosenblatt transformation was used to generate all samples with these dependencies and create the input space in unsteady case. After defining the environmental conditions in both cases, aero-elastic simulations are performed using FAST. This framework couples aerodynamics, elasticity, control, and hydrodynamic effects with different modules used to calculate the dynamic response of the wind turbine. As the wind turbine is represented as a beam model, the outputs are calculated in a node, not as a pressure distribution, and by default, only 10 nodes are defined per blade as a measure spot, and a total of 60 loads are extracted, considering forces and moments in all degree of freedom per each spot. With all inputs and outputs parameters defined, two different surrogate models methodologies are used. First, a Gaussian process or Kriging model is trained to predict the maximum load for both cases. A Gaussian process was defined per each output value. Second, a deep neural network is trained to predict all loads using one network. In the steady case, 1025 samples are used to train both models, and in the unsteady case, only 715 samples are used. All samples are generated using a single seed number, meaning that these results, to be representative of the maximum load value, needs to be run using different seed numbers that represent the spectral density function of the wind speed. For both surrogate models, the hyperparameters description can be found in the article submitted to the Uncertainty 2020 conference. To extract the maximum load value in both cases, the first 300 simulated seconds are neglected because the simulation tools start from a defined configuration point. When the pitch control of the blade starts working suddenly, generating an initial behavior that doesn't correspond to reality. To show the accuracy in prediction for both surrogate models, the relative error for each output is presented in both cases. In steady case, the Gaussian process shows a low error for almost all output values, but for some outputs, the moment in z direction shows a relative error of 0.1 or 10%. In the case of deep neural network model, the same response is found, but in this case the error can reach, for the same output, 0.175. In the unsteady case, the Gaussian process fitted also almost all outputs, but for some, the error could reach more than 0.8 or 80%, meaning a bad prediction for this output. On the other hand, deep neural network could predict the same output but with less relative error, equal to 0.46. This amount of error means a bad fitting of the output, but this error can be decreased by training those models with more data. As the objective of this study is to show the applicability of new methodologies to quantify the uncertainty, the use of deep neural network in wind turbine field will help their development thanks to the capability of managing high-dimensional problems with the computational development of GPUs, and compared to Gaussian process, this can take less time to train and predict. As future and ongoing works, a global sensitivity analysis of methods that are used to transfer the loads from Aero-elastic simulations to a 3D finite element model is performed, and then is used to select the one that introduces less variation to the output. Then, after this method is selected, is performed a fatigue analysis using deep neural network that will be used to analyze the reliability of the wind turbine blade. Thank you very much for your attention. Our references and more details can be found in the article submitted to the Uncertainty 2020 conference.